Yeah.
Yep.
Yes.
Very good.
Yes. We can hear you.
We can still hear you. You're good.
Yes, Professor, can you hear me? Probably my. Thanks. Yes. How about right now? Good. Yeah. I think. Yeah. Can I share my screen? Thank you. So can everyone see the slides? Okay, sure. So can I start, Professor? Good evening, everyone. My name is Rizia Chen, and today my topic for the presentation is formulation of flow and contaminant transport in unsaturated soil. My presentation will contain 8 parts. The first one, I'll give some background for the flow and contaminants in the unsaturated soil. And in part 2, I'll introduce some mathematical models. And in part 3, I'll put emphasis on the Richard's equations. And I'll show you how to estimate the hydraulic property in this topic. And I'll introduce analytic and numeric solutions. And part 6 is about the two-phase water airflow when the effect of the air pressure cannot be neglected. And the part 7 is solid transport for the chemical solutes. And part 8, I will discuss discussion and conclusion. So unsaturated soil is the soil whose water content is less than its porosity capacity. And as water transport and contaminant in unsaturated soils, the zone has been a major concern in several branches such as hydrology, agriculture, and environmental engineering. And those contaminants may contain liquid and solid waste disposal, fertilizers, pesticides, inorganic or the organic chemicals. So mathematical model being increasingly used to predict the water flow and the contaminants in unsaturated soil. And mathematical models can be formulated by a system approach and a physically based model. In system approach, we don't need to have a thorough understanding of the individual transport of particular solutes. It's more like gray box method, and the dynamic relations between the solute inputs and its downward movement are established in terms of impulse response function. For example, for the water equations, the epsilon t reference for the zero input response of the system. Tau is a solute input time, eta is a past input, and f is the impulse response function, which is time invariant. So if epsilon zero t is the state of the system without influence of the past solutions, and the integration term is the influence of the past impacts of the past solutions. So the state of the current system equals to the right hand side. Because all the transport and reaction combined with mathematical framework are under the condition of the conservation of mass principle. So the governing equations are always stemmed from the convection dispersion equation. The advantage is that each model parameters can be derived and tested individually, and model can be used to describe particular aspect of a system behavior. The limitation is that the parameters representations is always a simplification of the actual hydrodynamic or the reaction mechanisms. Let me take the Richards equation for example. Richards equation is a very popular equation to simulate flow in unsaturated zone. There are 4 assumptions whenever we are using the Richards equations. First, it's ignoring matrix and fluid compressibility, and the second one is the fluid density is dependent of concentration. Spatial variation in fluid density is ignored. Then the most important one is that the effect of the air pressure can be neglected. And if we write the forces on the viscous water, we can know that the total potential equals to the summation of the pressure potential, the solute potential, the electronic chemical potential, and the gravity potential. And we take the water head potential out, and we using Darcy's law, we can calculate the flux, and we combining the Darcy's law with the continuity equation, so we can obtain the Richards equation. And the Richards equations can be formulated in diffusive form and capacitive form. In diffusive form, the d theta is the diffusivity, and in capacitive form, the ch is the water content capacity. Now we have the equations, and we need to know the parameters in the equations, the water content theta and the hydraulic conductivity K. If we want to measure those properties, sometimes we measure them in laboratory experiment, but it's always expensive and time consuming. And besides that, it's nearly impossible to measure those hydraulic properties under the condition that the soil is unsaturated. So empirical models are often employed to predict those hydraulic properties. The 2 most popular models are VGM model and BNC model. In BNC model, a parameter related to air pressure is included. So now the equations are ready to solve. If we are if the solutions can be analytical or numerical, for analytic solutions, the governing equations and the soil hydraulic functions and initial and boundary conditions are very suitably simplified or approximated. let me take a one-dimensional convective dispersion equation, for example. With simple initial conditions and boundaries as this, the concentration as a function of z and t, the depth and time, can be written. It looks like this. So for a given time and for a given depth, we know the solute concentration. We know the exact solute concentration, and the limitation that is analytics solution cannot simulate, cannot solve for the complex condition. So in order to overcome the limitation of analytical solutions, numeric simulation becomes an alternative tool used in many researches. And the most popular methods are finite difference method, finite element method, and finite volume method. For one-dimensional Richards equations, the capacity form is written as this. And if we are using the implicit finite difference method to discretize the partial differential equations, we can obtain a format like this, and with all the parameters known, and we set the boundary conditions and the initial conditions, so the model is ready to solve in MATLAB. But sometimes the Richards equation is not very appropriate when the air pressure cannot be neglected. So we needed two-phase equation to describe the flow. So that's the reason why there is Richards equation can handle with the flow in one single equations. But for the two-phase flow equations, we have two equations. Here, W and A refer to the water and air phases, and phi represents the potentials, and the epsilon is the soil porosity, mu is the viscosity, S is effective saturation. But transport under field conditions generally requires a simultaneous solution, both of the unsaturated flow and the solute transport. Here I'll give a one-dimensional solute transport during the transient flow. The first term, phi S over phi T, is the exchange rate between the solid phase with the water. And the middle term, absorption term, and the last term is the sinks and sources. For equilibrium transports, a linear relationship is often assumed between the concentration of the solid phase and the concentration of the solution. So here K is the distribution coefficient. For the sources and sinks term, the phi is often approximated by a first or the zero order term. So if we substitute S and phi into the transport equations, we can obtain the solute transport model like this. It's very similar to the advection diffusion equation. For the non-equilibrium transports, the diffusion-controlled kinetic reactions can be formulated like the phi S over phi T equals to a function of S and C, and we substitute them into the transport model, and ignoring the sinks, the degradation term, and the model can be written as this. And two side and two region models will be included in the term paper because I don't have time to explain them in the presentation. And during the study, here are 4 conclusions I concluded. First is that the soil water is not simple water with several solutions. I think that soil water properties are linked to the chemical and physical properties of the soils. And the second, analytical solutions are useful in simulating hydraulic properties or verifying numeric solutions, but it cannot provide complete water profile and content in complex situation. The third one is about the Richards equation. This equation is appropriate when effect of air pressure is negligible, but when the effects cannot be ignored, a two-phase model should be considered. It should be more appropriate. So the most difficult term to simulate is the source and sink terms. So emphasis should put on to those things. and further some more detailed description of the flow and contaminants in unsaturated soil will be described in the term paper. And those are the references I used for the presentation. And that's my presentation. Thank you, everyone. For example, like the radioactive decay, or the solutes observed by the plant roots, like something is not included in the left-hand side of the equation. Because those terms are not in, for example, there is I need I think we should obey the mass of conservation. So I think those terms are not included. So if we don't have those terms, the left-hand side of right-hand side would not be equal. Yes. Yeah, we need um, we need like some submodels to represent those terms. Yeah. Yes, that's for sure. Yeah. Yeah, it's something like the chemical ring, chemical precipitation. Thank you. Yes. Yeah, exactly. Yeah. Thank you. Thank you. Thank you. So excuse me, any suggestions how to stop the sharing? Oh yeah, I see that.
I will be presenting the first part. Hi, Professor. Hi, everyone. My name is Haibe Abdi, and tonight we'll be presenting the topic of description of the determination of factor of safety using finite element analysis, and we'll also present some case histories at the end. And so we start with some concepts about general design methods for.
Yeah, you're missing the green screen, yeah.
I thought I did, so yes.
Oh, yeah.
Can you see my screen, Professor? Sorry about that. So if I start with some concepts about the design methods for geotechnical engineering designs, majority of the geotechnical design codes are based on limit state design concepts, which define limits in which structures are safe and fit for use. So that would be serviceability limit state and ultimate limit state. For serviceability limit state, this finite element is well suited for finite element analysis, well suited for determining displacement using finite element displacement method. But when it comes to ultimate limit state, it's not straightforward as it would be for SLS. And that's mainly because that we're dealing with material behaviors such as the yield strength and the failures of the soil and the structures that are involved in the design. So, and also the fact that for SLS or the serviceability limit state failures, these occurs in conditions where the structure experiences during the service, while ultimately failures normally occurs at an event where it's mostly unlikely to happen. And we have to manipulate the model to fit that conditions where the failure occurs, depending on the material strengths. There are many advantages for using finite element analysis for designing geotechnical structures. Few of them are we could have simultaneous checking for limit states in multiple forms. We could also check for serviceability limit state and ultimate limit state with one analysis model. And using finite element analysis, it considers the flexibility of the structure and the soil structure interaction effect on those limits. Since ultimate limit state is a little bit more challenging to not straightforward as the serviceability limit state, there are two approaches where we would introduce safety factors to the design, and these two are input and output factoring approaches. For inputting factor approaches, it is suitable for problems that involve equilibrium of the ground, such as embankments, slopes, and retaining structures, while output is suitable for structures that face interface failure types, such as piles and ground anchors. And when we're doing input factoring, we would factor ground strength, and we would also factor the structural load or any variable load such as back loads. And for the water levels, we will take into account the worst case scenarios. While if we are factoring the outputs, we will But we will take all the inputs without any factoring except for variable life loads, and we will factor the loads, the structural loads, and geotechnical loads that are applied to the structures. And here you can see that structures like slopes and retaining walls, which are mainly governed by internal loads causing ground failures, input factoring would be suitable for those kind of structures, while structures with external loads and interface failures like piles and anchoring, ground anchoring would be suitable for output factoring. And when we have structures like spread footing that have external loads, at the same time we would also face ground failures, either one would be sufficient. Each of these approaches have their advantages and disadvantages, so another approach for combining the two would be suitable to make sure that we take into account and we are looking at all aspects of the failures area, and we compare whether input factoring or output factoring would be the more critical, result. And there are two types of factoring using both approaches, or dual factoring. One would be factoring the input from the initial state, and that factor will be later taken into each stage of the construction. And this would be an easier approach, but it also would give us an unrealistic results, because as we factored from the initial state, which might not be true to the initial stresses of the structures. Another approach would be dual factoring approach using strength reduction. In this approach, ground strength and all the water levels would be unfactored from the initial, and factors would be taken into account at each construction stage level. Loads would be factored, and structural loads would be factored, while ground strength parameters would be reduced, and this would give us a more realistic result to analyze. And these are the kind of approaches that different sectors use to analyze and find a factor of safety. And at each stage, there will be a check for the ULS and to confirm where the failure occurs. And now I would like to welcome my colleagues there to take on the next part.
Thanks. Hi, everyone. I'm Gina Rezvani. Due to the complex geometries, loadings, and material characteristics, the analytical mathematical solutions typically demand the solution of ordinary or partial differential equations, which is actually not possible. Therefore, in order to find a workable solution, we must rely on numerical methods like finite element method. Instead of needing the solution of differential equations, the problem's finite element formulation yields a system of concurrent algebraic equations. These numerical methods produce approximations of the unknown values at discrete locations along the continuum. Therefore, the act of representing a body by breaking it up into an equivalent system of smaller bodies or units, which are finite elements, linked at points linked by two or more elements, boundary lines, and boundary surfaces is known as discretization, as you can see in this picture. In fact, thanks. In fact, in the finite element method, we developed equations for each finite element and then combine them together to get the answer for the full body, instead of resolving the problem for the whole body in just one step. Next, please. An assistance in representing and resolving an algebraic equation system is a rectangular array of quantities organized in rows and columns known as a matrix. As you can see here, examples of matrices include the force components operating at different nodes or points on a structure and the corresponding set of nodal displacements that can be expressed as F and D matrices, and also the element and global stiffness can be represented as matrices. As you can see here, the small k is the element stiffness matrix, and the capital K is the global stiffness matrix of the body. The global stiffness matrix is used to correlate the global nodal forces F and the global nodal displacements D by this equation. This equation, which is often known as the global stiffness equation, symbolizes a collection of simultaneous equations. It is the fundamental formula used in analysis using the stiffness or displacement method. Next, please. Generally, we can divide the finite element stability methods into two categories. The first one is the enhanced limit method, which is actually a combination of finite element analysis and limit equilibrium method. In fact, in this method, we calculate the stresses at each point in the soil mass using finite element analysis, and then import these calculated stresses into a limit equilibrium method to find the total factor of safety for the soil. Several researchers have studied this method and proposed different formulations for the factor of safety, as you see here. And the second category is direct method, which uses only finite elements. This method is based on the concept that we increase the load or decrease the strength of the soil until the failure happens in the soil. Next, please. Here you can see the calculation to find a factor of safety in enhanced limit method. First, we use the computed stresses in finite element analysis to find the local factor of safety values, and then use these local factor of safety values to find the global factor of safety for the slope. Next, please. And as I said before, using finite element analysis, we calculate the stresses at each specific point and then find the applying normal and shear stresses and also the soil strength at each point, and then employ these information to calculate the factor of safety for the whole body. Next, please. Three problems need to be addressed in order to carry out the interpolation and determination of the stress at each specific point. First of all, considering a general point represented by its Cartesian coordinates, the element which the point belongs must be determined. In the next step, once the element has been determined, the point's local coordinates should be calculated in order to assess the interpolation functions. And finally, the element nodal values of the stress components should be discovered since these are typically calculated at Gauss integration points. Next, please. In direct method or the strength reduction method, the critical slip surface is found automatically from the calculated shear strains. And in this method, the perfectly plastic Moore column model is used. And a number of separate finite element analysis must be done to obtain the factor of safety and a slip and critical slip surface in this method, which are actually more time consuming and also sometimes more expensive than the other methods. As you can see here in these equations, the strength reduction method's definition of the factor of safety is the ratio that must be used to divide the original shear strength parameters in order to reach the slope's failure point. Now my friend Mudassir will continue.
Hello everyone, my name is Mudassir Noor. So I'm just going to elaborate a little bit more of what Zina was explaining earlier. So the finite element method usually exhibits the deformation analysis. So the idea is to have boundary value problems, and you approximate those and discretize them in a smaller discretized mesh. So the idea is to make sure that you have the geometry discretized in smaller components and smaller pieces, such as the mesh. The idea is to have the main quantities interpolated over the elements, and based on those value points, you form your stiffness matrix and the so-called force vector. So the idea is to have a global solution, which is force is equals to K times T, which would be your force vector, which would basically be equivalent to your stiffness matrix multiplied by the global displacements that you calculate over the nodes. Next slide, please. So the steps in the finite element is usually to establish the stiffness relations for each element in each small mesh that you've created. Material properties and equilibrium conditions for each element are used and established for that case. Then you have to enforce compatibility of these elements. That is, you have to make sure that all these elements are interconnected at every node. Once you have the equilibrium, you have to enforce the equilibrium conditions on the entire structure, and in the present case, for the nodal points. Using these two steps, this is known as assembling. Once you have the assembling done, you inhibit the boundary conditions, you enforce the boundary condition, and you solve for the system of equations. Next slide. So the discretization can be done in two separate elements, in two different formats. One is a triangular element or a quadrilateral element, such as the Lagrange elements, as shown here. You can see there's so many points in that triangular elements. The only advantage is that when you have a triangular element, you can have straight lines wherever you feel that the property or the material or the shape of the structure is curving. You can add additional points between the straight lines, as you can see here in the triangular elements and in the Lagrange elements here as well. Next slide. So you create the element and the shape functions. So for example, in this case, you have a triangular element. You can establish the displacement in the form of u and v, in this case x and y, globally. You would set up a system of equations. So for example, in this case, you have the three nodes I, j, and m. You would establish the nodes, the resultant displacements in the x directions for I, j, and m nodes, and the I, j, and m nodes in the y direction. Once you set up the vector, the matrix, you would find the you would establish the formulation, such as where you can see the n matrix, which will now be known as the shape matrix. Next slide. So once you have the displacements are usually the derivation of the displacements would give you the strains. It is a simple analysis for this. You just derive you do the derivative of the x direction equations and the y direction to get your strains in the x direction and the y direction. And in this case, x and y is generally the principal stresses, and x and y, xy would be your shear stress strain. So you can establish for all three of them. As we have seen in the lectures earlier, the element is usually a Cartesian stress tensor is usually composed in a vector. So you could have, as you can see in the diagram, you can have the principal stresses, which are in the x direction and the y direction. And in case of a 3D element, it could be in the z direction as well. And you would have the subsequent xy shear stresses. The stresses sigma are related to the strains with this format, which is stress is equals to C times epsilon. And in a geotechnical realm, the C value is the material stiffness matrix and the material behavior. Next slide. So based on the Hooke's law that we've seen, F is equals to minus KD, we can see the basic parameters in a geotechnical problem. What we're looking at relatively for soils would be the Young's modulus, or the modulus of the soil and the Poisson's ratio. In the geotechnical analysis, you would use the shear modulus, the bulk modulus, and in case of a 1D analysis, you would also use the odometer modulus. So the stiffness matrix for this case would look something like this, where you have the use of the Young's modulus and the Poisson's ratio, and you can see it's a symmetric matrix. Next slide. And finally, you would come up with you would solve for the global stiffness. You would solve for the global equation, which is F is equals to minus KD, which in this case, your F would be yielding the stresses in the X, Y, and Z direction. For example, this is for a 3D element. So you would have it in the X, Y, and Z direction, which is equal to your stiffness matrix, which has already been established, multiplied by the strains, which you get based on the displacements that you've exhibited in the finite element model. Now I'll pass it over to Desmond, who would go over the case studies. And yeah, that's about it.
Yeah, starting with the first case study, where we will be considering a cohesive friction soil with a weak layer of 0.5 meters. In finite element analysis, the strength reduction technique was implemented in this case study to obtain a factor of safety. The steps are described below and as illustrated in the following figures. Step 1, first we calculate the available strengths, CA and phi A. CA is C all over an initial factor of safety, which is F0, which is considered as 1. Then phi naught is equal to, represents the tan inverse of tan phi all over phi naught. Then from finite element analysis, the mean unit weight of the soil is computed using upper bound and lower bound theorems. Subsequently, a gravity multiplier M0 is computed. In the third stage, if the gravity multiplier is less than 1, a change in factor of safety is set to a -1. Otherwise, a positive 0.1. A new factor of safety, which is F1, is equal to F0 plus change in F, is obtained. The step is repeated with the new factor of safety, F1, by computing the available strength again. This is an iterative process. So with the available strength for C, now it is C all over the factor of safety 1, not the initial factor of safety. Then phi, the available strength for phi A is equal to tan inverse of tan phi all over F0. Then the second step is repeated. In the fifth step, if the difference, the M1 minus 1, the product of M1 minus 1 and M0 minus 1 is greater than 0, then the factor of safety is linearly interpolated according to this relation given. This procedure is described in the following figure. The following figure to the left represents the initial factor of safety. The factor of safety, the trial factor of safeties are on the x-axis and the gravity multiplier on the y-axis. First of all, we tried a factor of safety of 1, which yielded a gravity multiplier of 2, which is greater than 1. Then we are looking to approach a gravity multiplier on the unit weight where it is equal to 1, that is M is equal to 1. So we add a 0.1 to our factor of safety, which gives us a trial factor of safety of 1.1. And in that trial, we obtained a gravity multiplier of 1.477. We again add a change in factor of safety, the next trial, which is 1.2. Then we try, then our gravity multiplier yielded 1.1, which is again greater than 1. Then until our gravity multiplier equals 1, there we obtain an optimum factor of safety for the slope considered using the strength reduction technique. In the figure to the right, at M is equal to 1, the deformation is seen to form along the weak layer, where our factor of safety is obtained as 1.27. I will hand over to my colleague to discuss the next case study.
Good evening. My name is Ola, and much has been said by my previous colleagues on the mathematical expression of this. The case study I'll be presenting tonight is related to the railway slope in Moroccan Reef between Tangier City and Tangier Mediterranean Port, as shown on the map. So the geological mission of this, the Tangier area where the railway failure occur is as shown on the left side of the slide. There are field test and laboratory parameters were taken, and a geometrical model obtained, and calculations were carried out based on this profile you can see on the top. Then next slide, please. Calculations are carried out under two following conditions: dry state and saturated state. Initially, for this study, 3 softwares were used for this computation and simulation: the Placis, GeoSlope, and Terran. But for the sake of this study, I limited to the Placis. Next slide, please. Okay. Then for the dry state condition, share strength reduction method according to the mole column criteria underestimate factor of safety by 2%. Can you go back to the previous slide? Sorry. In the top geometrical model that was simulated for the dry state condition. The bottom one is about the saturated state condition. Were carried out by supposing that the pore water pressure are uniformly null in the slope. The presence of water table destabilize the slope and reduce the factor of safety. Can you go to the next slide, please? Okay. Then in this this model, the determination of factor of safety insufficient, like using the analytical method, but for the finite element method, you're able to predict the actual settlement based on the displacement and be able to optimize way of reinforcement and also prediction of failure mechanism, as well as the field and laboratory tests obtained to better approximate the real behavior of the structure. Thank you. This diagram here, the top one shows the strain relationship in the blue circular curve, and the base one shows the localized plastic zone. Thank you. And these are the references. Thank you.
Anybody wants to take that question, or do you want to take that question? Desmond, do you want to go for it?
I didn't actually get it clear. So can you please repeat it?
Why do you use finite element for the?
Okay, more recently, due to the enhanced capacities of personal computers and considering the factors finite element takes into consideration, like stresses of, let's say, the structure or slope or the civil engineering structure, which other methods do not really consider, such as the traditional limiting equilibrium. Deformations are not really considered in the traditional limiting equilibrium, but in that of finite elements, all is considered. So using the finite element method is more a representative form of simulating the strength or the stability of the particular civil engineering structure being considered.
And also to buttress the fact of what he has said, for the analytical method, the factor of safety are always assumed constant along the failure zone. But in this, for the finite element, we take in of more parameters of the geotechnical parameters like the field test in the computation, and it gives a better picture of to predict the failure mechanism.
And to add to both my colleagues, there are valid points there of why to use the finite element versus regular limit equilibrium methods. Is that, like they said, there is some drawbacks to that as well, because, for example, using the shear strength technique, reduction technique, it's already been established in research and in the industry that in order to get more meaningful results specific to this type of problem where you have the slope stability analysis issues, there are certain conditions that should be met. So, for example, the example of the setting up the matrices where we said the modulus of elasticity should be the same pretty much for all the materials. A valid single Poisson's ratio should be used. The dilation angle should also be used, should be assumed to be zero in this case. And you can always use only elastic plastic condition, which is for the post-peak behavior. So there are some limitations to it, but the limitations usually outweigh the pros now that you have enhanced capacity, and you can see the state of the state of the soil compared to what you would have within a limit equilibrium, because the limit equilibrium does not take into account the history of the soil. In this case, it does take care of the history of the soil.
And I want to also add to my friends what they said, that in a limit equilibrium method, we actually have some assumptions in the first step to solve the problems, specifically for finding the critical slip surface. But in finite element, we don't have those assumptions, and we can automatically find the critical slip surface.
And in all, when you do both, sorry to add another thing there, both the factors of safety are pretty much the same. So in the industry, you would still end up using limit equilibrium because it's more cheaper compared to having a finite element analysis. It's time consuming to do that compared to a limit equilibrium.
Just left.
You could use. Sorry, you want to go ahead, Jasmine?
Hi.
Sorry, yeah.
No, you talk. It's okay.
No, that's fine. It's okay. Sorry, the question was specific to using the finite element method. Yes. 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 Mm-hmm.
Yes. Yeah. Maybe considering the type of structure and whether it's a long-term or a long-term like case or a short-term case. Then for a long-term scenario, one would consider, a practitioner would consider going with the finite element analysis.
Correct.
Rather than the limit equilibrium method, which maybe is more suitable for short-term analysis.
And also the finite element is able to predict vividly the complex structure, unlike the analytical method.
Yes. So in a case where we had to put in for example, if I have to put a pine in the slope to stabilize it, yes, we would recommend to use a finite element method to model it, because to modeling a 3D element into a limit equilibrium problem is always time consuming. So in that case, yes, you would use that.
Another thing to consider, sorry, can you hear me?
Yeah.
Yeah.
Yes, another thing to consider is when using finite element analysis is would we be able to justify the extra load of work or the cost of that loss of force, and that we cannot, that looking at the complexity of the project, that we cannot get reliable results. So if it's a small project or for a certain foundation of a building, or that can be found using regular general methods according to the course, we would prefer doing that. But once we can justify that extra cost and time, then those are the kind of projects where we would be able to use analysis.
I did a competitive, just for your information, I did have at the end of the slides, we actually did run another few cases to show you how the limit equilibrium fares versus a finite element. We ran a couple of cases ourselves to show how complex it can get, so.
Yeah, because we had a limited time.
Yeah, so I put it at the end of the
You're already about 25 minutes.
You're
Thank you.
Thank you.
Thank you.
Hi, everyone. Are you guys able to see our screen share / your voice?
Yeah.
Yep.
Yes. Okay. Awesome. So let's move on. All right. So our topic was analysis of earth retaining structures using finite element and finite difference approaches. So to begin, we're going to be first introducing retaining walls. Then we're going to be going over lateral earth pressure. We're going to go over Coulomb's method and Rankine's method, as they are the two methods that we are going to be analyzing. Then we're going to analyze the design of retaining walls, as well as discussing finite element and finite difference approaches. All right. So what are retaining structures? Retaining walls are constructed to do numerous things, such as retain earth, water, or other materials, to resist lateral earth pressures, to resist movement of the backfill, to stabilize the hillsides, and to control erosion. Now, there are different design approaches, such as the finite element method and finite difference method, which will be discussed in this presentation. All right, so starting with lateral earth pressures. For lateral earth pressures, they're designed to be either at rest, active, or passive. These are the three cases that we have. So when a retaining wall remains fixed, and it's at rest, Pn and P naught is equal. When it's inactive, we have retaining wall moving away from the soil, and when it's passive, it's getting pushed towards the soil, or the backfill in our case. Moving on. So now we're going to be discussing the active condition. So you have the lateral active force formula over there at the top. And afterwards, using Coulomb's active earth pressure coefficient, we get the K formula, as you can see, and we have the general case right below. So moving on, we're going to discuss the passive forces. So again, you have the passive force formula at the top, then using Coulomb's passive earth pressure coefficient, we get Kp, as well as the general equation, which we have at the bottom. So moving on, we're going to be discussing the Moore Coulomb failure. So you will be able to see how we have our lateral active forces, and then using Rankine's active earth pressure coefficient, we get the K formula, as you can see, as well as the general case. Now we also have the passive condition, for which, again, we have the lateral passive force and the Rankine passive earth pressure coefficient in both the general case and the case above. All right, so now we're going to consider cohesion, the effects of cohesion, for which we have our lateral earth pressure, our lateral active force, as well as the depth of the tensile crack. Moving forward, we're going to talk about the design of retaining walls, for which there are two major aspects, the external stability and the internal stability. So external stability is the cases that we're trying to avoid, such as overturning, otherwise known as rotation. It's the first case you see on the left. And then we're going to have sliding, case B, bearing capacity or settlement, as well as deep-seated shear failure. Now discussing internal stability, we have some other cases in the bottom for which we can add more structural stability for our wall. Now discussing a factor of safety for overturning, sliding, and bearing capacity failures, we have the formulas over there. And so now we're going to move on to the finite element method. So the finite element method is a numerical procedure for obtaining a solution, or otherwise an approximate solution, to any physical problem governed by differential equations. Now, this is only when analytical solutions are not readily available. Now, we are going to be discussing discrete element formulation as well as continuum element formation. Now, in the discrete element formulation, we obtain joint displacements and member forces of a structural framework in terms of a matrix analysis. And in the continuum element formulation, we obtain approximate solutions at specific points or nodes. And moving on. So in the discrete elements, their geometry is defined by local coordinates. We have cross-sectional properties, area, and moment of inertia. And these elements are connected only at common nodes. You have a diagram at the bottom showing trusses, beams, frames, and grids. You can see how there's 48 elements, 28 nodes, and 6 degrees of freedom. So for moving on to the continuum elements, now these are defined by 3 or more nodes, and elements connected at common nodes and are along common edges. Compatibility of enforced at nodes and edges, trusses, beams, frames, and grids. So you have a diagram explaining the following. And moving on, we're going to go over the steps of the finite element method. So the first step will be to discretize and select our element types. So we divide the body into equivalent systems of finite elements with associated nodes, and we choose the most appropriate element type. We have some element types at the bottom for you to take a look at. Now moving on to step 2, this is where we select the displacement function. We choose a displacement function within each element using nodal values. They can be linear, quadratic, or cubic polynomials, which are most common. Step 3, compatibility and constitutive equations. So here we relate strain to displacement through compatibility equations, and we relate stresses to strains Moving on to step 4. So now we derive element stiffness, the element stiffness matrix and the equations, for which we have the main equation right under. And in step 5, we assemble the element equations to obtain our global or total equations. We introduce our boundary conditions, obviously. And in step 6, we solve for the unknown displacements by imposing our boundary conditions. We solve for unknown degrees of freedom using these boundary conditions. And in step 7, we solve for the element strains and stresses. And in step 8, we interpret and analyze these results. So why would we use finite element method? So we use finite element method for irregular shaped bodies, for general loading conditions, bodies of different materials, element equations. They are evaluated individually. It's used for when we have mixed boundary conditions or nonlinear behavior due to large deformations and nonlinear material. Steady state and time-dependent problems are also a case where a finite element would prove to have an advantage. So for our finite element method, basically what we have here is a little diagram that shows our steps. So for here, we're going to be starting with our external displacements or deflections, and using our compatibility equations, we're going to get our strains and stresses. And from there, we have our internal member forces, and we're able to get our external forces or loads. All right, so in the finite element method, we can use the displacement or stiffness methods, and we're going to use them to derive the element stiffness matrix equations, and different methods that are used to obtain the numerical solutions to our differential equations for frames, for 2D or 3D problems. Now, we can either have variational methods, such as the theorem of minimum potential energy or the principle of virtual work, as well as weighted residual methods, which includes the collocation method, the subdomain method, the Galerkin method, and the least squares method. So we're going to be focusing on the theorem of potential energy, minimum potential energy, as well as the Galerkin method. So the theorem of minimum potential energy. So the displacements at equilibrium position, they occur such that the potential energy of a stable system is at minimum value. So if we have our strain energy and our potential energy of external forces, the sum of them come to our minimum value. Now, the Galerkin method is an approximation solution for the differential equation that you see at the top, and the simplified approximate solution is in the blue box right below. So Farbod's going to cover the next slides.
Thank you, Arif. My name is Farbod Azimi. I want to continue the finite element method. We are using the stiffness method for frame elements for 2D and 3D analysis. The Euler-Bernoulli theory is used for analyzing the frame elements. As you can see, these are the differential equations that obtained from the Euler-Bernoulli theory. Here is the stiffness matrix in global, and you can see here the global nodal forces which are related to the disassembled stiffness matrix, and here is the degree of freedoms of the system. The second one is 2D or planar elements, as you can see, based on which element type that you can choose. Here you can different degree of freedoms, and at first step we should assume a displacement function as here. As you can see, these shaping functions, matrix, and here is the DOFs. So in the next step, we obtain the strains using the derivatives of those shaping functions as a matrix form divided by multiplied by the degree of freedoms. You can reach the strains, and then using the strain-stress relationships to find the stresses. And here is the stiffness matrix and other nodal load vectors and the others. So now we're gonna focus on implementing the finite element method in retaining structures. All these earth retaining structures can be divided into three categories: the gravity earth retaining, reinforced concrete earth retaining structure, and embedded earth retaining structure that we want to discuss and focus on this, the third one. So the earth pressure that can be calculated in some earth problems of retaining walls, the distribution of the earth pressure on the wall can be obtained from different methods. And here is some considering, as we have to consider the wall friction, the mode of wall deflection, and stress strain characteristics. And I will discuss these three categories. The wall friction is exactly the interaction between the wall and the soil. So to come up with this issue, we consider an elastoplastic joint element which can be provide us with the mechanical behavior of the at the interface, and for doing this phenomena, the shear normal stress ratio on the interface of the wall and the soil we consider equal to the tangent theta delta, which is the coefficient of friction. The second one is the modes of wall deflection. We can consider different modes of deflection for the wall. As you can see, 4 types of deflection can be considered in active and passive state. The third one is the stress-strain relationship or constitutive equation. Based on the concept of the spatially immobilized plane, we can consider some characteristics of stress-strain behavior of the soil. So using the joint elements and these constitutive model, we can find the active and passive earth pressure using the Rankine and Coulomb method, as RF explained it before. As you can see, the factor of safety can be obtained. So here is the case study of the active earth pressure problem, considering the only wall deflection without considering the interaction between the wall and the soil. As you can see, by considering different deflections, we will come up with different lateral pressures. These 2 cases are distribution of horizontal earth pressure in active state. But if we want to consider the wall frictional angle, interaction between the wall and the soil, we can come up with another distribution for horizontal earth pressure. So what we do a model on the slope software using the slope W. We use the 3 kinds of soil, the backfill and 2 others. And finally, we find the safety factor of 1.8 for this specific problem. So moving forward to the finite difference method, it's another numerical method that provide us with finding some approximate solutions to solving our differential equations. And as previously mentioned, we can use Rankine method and column method in this method as well. You can see some procedures of this method based on the Rankine method. You can develop the BM ratio, the ratio BM to the shear. BM is the bending moment, and the SF is the shear force or the ladder force. And as you can see by defining the boundary conditions, as you know, we don't consider that we don't have any bending moment and shear forces at the top of the retaining structure. And here is the procedure. As you can see here, we can find the moments and as well as the shear forces using these formulas. For each layer, which or each elevation, you can use the previous layer in order to find your specific moment at that level. And here you can find the shear forces as well. You can see it's like a case study that shows the bending moment versus depth and shear force versus depth. Here is the wall structure, and the variation as is shown here. And for the column method, if we cannot solve using the Rankine method, or we cannot satisfying Rankine assumptions, we use this kind of method. Similarly, in this case, we should consider the sliding force, and we can find the bending moment for each elevation using the previous layers. As you can see here, we can find the moments and shear and the sliding force for each specific level. Thank you, everyone. That's all our presentation.
No, you should.
We know that we use the finite element method as a method in order to solve the differential equations by making some approximate solutions. It's easier when you make some approximations, and you can come up with the very similar results that we can compare with the exact solutions. The finite element results is really similar in most cases. It's similar to the exact solution. It's simpler way of doing all those differential equations, which it's really hard to solve using the other methods. It's come up with and help us to make it easier to solve all those differential equations. And Arif, if you can add.
Yeah, just to add on what Farb was saying. So basically, when we have very complex cases or there are a lot of factors that we have to consider, it's a lot easier to use finite element method or finite difference method or associated softwares in comparison to doing it all in the traditional way. And also using these softwares in finite element or finite difference, the benefit is that you don't have to have necessarily all these other assumptions that you would make. It can be very close to the realistic case. So yeah, it would be simpler. Well, kind of like what Farbat said, you still can achieve the results with traditional techniques. It's just significantly more time consuming and there's so many errors you could make. So that would be a benefit to doing this. So I would say it's just a lot more time efficient and you're guaranteed to have correct results. Considering you are able to analyze and make sense of it.
And in the classical methods, at the first step, you should consider some assumptions for finding all those deflections, the forces. But in the final element method, all those things, all those elements, automatically based on the element type that you have chosen, and for the other elements such as surcharge or the levels of different soils, you can find the exact failure, I mean the slip failure for your trench. Exactly. Yeah.
I would believe it's probably on the larger side, just because it considers more aspects. But yeah. Sure.
Yes, exactly.
Thank you.
Thank you.
Hello, everyone. I'm Zainab, and I'm going to talk about the formulation and the solution of coupled thermal hydraulic problem in geotechnical engineering. And first, we'll start with a brief introduction about the problem that we're going to solve it, and after that, we'll explain the coupled thermal hydraulic. Oh.
Slides, you're not showing the slides.
Not.
Yeah.
Click to this.
Is it okay now?
No.
But I should.
Share your full screen, not just a specific window.
To the
Let me
slideshow.
stop sharing and then.
Yes. Reshare.
Oh. I don't know what's just.
Yeah, but it's true that you have a started screen sharing.
I already share my screen, but I don't know what's. I know. Okay, so. Is it okay now?
No,
Yes.
no.
Oh my God.
Just do that.
Yeah, I think.
You can try Control and S. Try this one.
To what?
Control and S.
Control S.
Yeah, Control S.
Control S.
Yeah.
It's not changing anything. It's my screen is locked now. I don't know. I mean, maybe.
Yeah.
How do it?
So, yeah, but my screen is locked now. I can't even see. Yeah.
Oh my God.
Okay.
Yeah, so I can't change anything as I'm on the first slide. So I press everything. So I don't know what's going on. It's the first time it's happening to me.
Oh.
Maybe.
Yes.
Yeah.
She can exit reboot.
You can restart your computer, maybe.
Yeah, exit reboot and you get to come back.
Yeah.
Yeah.
Technical problem.
Professor, just to give you an idea on the deformations that you were saying earlier, right, the order of magnitude is almost twice when you do it regular deformations on the retaining walls. We've done the regular hand calculations are way off. It's very crude. This gets you with a finite element, like the forces we usually calculate are in the order of 2 in regular PY wall analysis compared to a finite element analysis. So it's a bit more complex. I guess it takes into account very minute details. So the approximations are pretty good. Mhm. Mhm. You have cohesion too. Mm. Yeah. Yeah, but it, like I said, it's very taxing on the economics of this stuff.
All right, okay now.
Okay.
So is it okay now? Are you?
Share your whole. Share your whole.
Good,
Yeah.
good, good. It's okay.
Yeah, it's okay.
So I'm sorry for the inconvenience and wasting the time. Yeah, maybe.
Yeah.
Okay. My name is Zainab, and I'm going to talk about the formulation and the solution of coupled thermal hydraulic problem in geotechnical engineering. And first we'll start with a brief introduction about the problem that we are going to solve it, and then is the formulation. And then we'll talk about the coupled thermohydraulic boundary condition. And the important part is to know how to calculate the stability of the time integration scheme as an important time in integration scheme. And finally, the outcomes from the analytical investigation are utilized in simulation of an open loop ground source energy system. So in recent years, ground source energy systems such as open loop systems have become increasingly popular because it is sustainable, it is renewable, and with less impact on the environment. And so as a result, it is so important to know how to solve the geothermal, how to solve this problem and how to model the geothermal systems. Before using the numerical method, to simulate an open loop system, let's know basically what is an open loop system. As it can be seen in this schematic picture, there is a supply well and also there is a injection well. These geothermal systems are utilized to capture and or move heat from and into the ground directly, capturing water from an underground source into a well and sending it back, to another well which is located at a different location. And open loop system, there are different systems, but the open loop system in comparison other systems like closed system is more efficient. So that's why I'm talking about this particular case. So in this particular case, in order to simplify the problem, we're assuming that the fluid is non-condensable. So the continuity equation defined by equation number 1 must be met by non-condensable pore fluid flow and the soil as a fully saturated porous medium. So in this equation, the nu, x, y, and z are the components of the velocity in different directions, and the epsilon nu is the change in volume divided by the original volume, and the q is represent any, like all pore fluid sources, and the t represent the time. In order to calculate the govern the formulation for pore fluid flow, we can use the Darcy's laws. First, to govern the seepage velocity. In a coupled thermohydraulic problem, regardless of the effect of the temperature gradient on a pore fluid flow in a completely saturated soil, and by assuming that the soil skeleton is rigid and it's non-condensable, the seepage the steady state seepage equation can be written as equation number 3. And as I mentioned before, this is a coupled thermohydraulic problem. So in this problem, so we need to govern the both pore fluid flow formulation as well as heat transfer. So in a fully saturated soil, heat transfer modes are conduction, convection, and radiation. Regardless of the effect of radiation in comparison of conduction and convection, which is not considered in this formulation. So here we're just talking about the conduction and convection and its impact on an open loop system. And due to the law of the conservation of energy, the equation heat transfer can be expressed as equation number 4. And in this equation, phi theta is heat content of soil per volume, and then q theta is heat flux per unit volume, including is a sum of the both conduction and convection. And also we have to calculate the heat source as well, and then the dV is the volume of the soil. And as I mentioned before, we need to calculate the heat source, and then we can use the equation number 5, which is the assumption the heat source in both water and the soil part, and soil particles. And here CPW, CPS are the specific heat capacity of pore water and the soil particles, and then rho water and rho W and rho S are the density of pore water and the soil particles, and N is a porosity, and then T is temperature. And then we're assuming that the thermal equilibrium is assumed for this equation, so that's why the T is here, and then we don't have a specific T for each different parts. And heat flux term, Q theta in equation 4 can be written as the sum of as the sum of the QD and QC, which is conduction and convection. So we can see in equation 7 and equation 8. So if we rearrange equation number 4 with equation number 5, 7, and 8, we can govern the equation number 9 finally, which is the equation of the heat transfer. So and finally, the combination of the equation of the equation number 2, 3 and 9 leads to the finite element formulation for coupled thermohydraulic problem. This equation is the seepage present the seepage velocity, and equation number 3 was the steady state seepage velocity, and this equation was the equation of the heat transfer with both for both conduction and convection. To validate the coupled thermohydraulic finite element formulation, several analyses on a 1 meter soil, 1 meter bar of soil with element lengths of 1 centimeter, subjected to 1D convection dominant heat transfer, were conducted in Imperial College Finite Element program using four noded linear quadrilateral two-dimensional elements. So here you can see in this picture the geometry of the considered problem, and in this table the material properties in this case. So a boundary condition was developed by a constant pore water pressure gradient over the mesh and applying a pore water flow from the left to right with a constant velocity, and applying a 10 degrees centigrade as an initial temperature, and a constant temperature boundary condition of 20 degrees centigrade to make a temperature the temperature difference, the temperature gradient at the left side of the bar, and then the time step was 60 seconds to simulate the case that we see in the slide. So this equation can be used to calculate the total amount of energy associated with the flow of pore water through the boundary. This boundary condition is nonlinear, so because both temperature and velocity are nonlinear, so are varying. So that's why this equation is nonlinear. So therefore, it is a definition of the coupled thermohydraulic boundary condition. And then, as I mentioned before, the nu is the velocity of the pore water flow through the boundary, and then T is the current temperature of the boundary. And the omega denote either a line or a surface or a volume over which the boundary condition is prescribed. In coupled thermohydraulic problem, it is essential to define a time integration scheme to estimate the numerical solution over time, stepping delta T in the finite element analysis, and the stability condition are the important part of any time integration. If we use stability time stepping, the errors between the numerical solution and the exact solution can either decrease or remain, or at least remain constant. So for 1D soil bar in the X direction, without a heat source and with just the temperature difference, we can summarize equation number 9, which was the equation of heat transfer, as equation number 11, due to the assumption that I mentioned. And all components of these equations have been defined in the previous slides, and the theta method is utilized to calculate the equation of coupled thermohydraulic problem in this case, and also it is important to govern the conductive convection heat transfer. An eigenvalue analysis is required. Using the Galerkin finite element method to discretize equation number 9, the heat transfer equation leads to equation number 12 in this equation. And the C is the mass matrix, which representing heat content. The K is heat conduction, and the D is heat convection. And if we put the equation number 13 and 14 should be the modulus of the matrix be calculated with equation number 16, and the modulus of the value of matrix B should stand or equal 1 to being sure of the stability of the time integration scheme. Actually, I will ignore the rest of calculation for eigenvalues for me, because it's going to take so long, and I've just present the results of the results here. The results are if the theta would be between 0.5 and 1, the algorithm is unconditionally stable. But for the theta less than 0.5, the algorithm is stable provided that delta T less than H2 divided by 6 alpha multiplied by 1 minus 2 theta. And the components are presented here, and the cos theta is the thermal conductivity, and then rho and Cp are the density and the specific heat capacity of the soil, and the H is the element length, and then for the alpha in this case, to reach the theta less than 0.5, we can calculate that with this equation. So the Berkeley number, or PE number, describes the ratio between the convection and convective and conductive heat transport. It's first that, like, if for a low PE illustrate that the conduction is dominated, and a high PE shows the flux is dominated by the convection. And then using this formulation, we can calculate the PE number. And this formulation, rho as rho W is the density of water, and then CPW is the specific heat capacity of water, and then the nu W is the velocity, and then L is the length of the in the direction of the fluid flow, and then the cos theta is the thermal conductivity. Here we can see the effect of PE number on the solution of convective problem with coupled thermohydraulic boundary condition. So in the figure number 1, both figures are with linear elements, and the left one is for the coarse mesh. As we can see, the PE number is 60 for that case, and for the right one is the fine mesh, and the PE is 16 in this case. These figures show the temperature distribution along the soil bar at different stages of the simulation with linear elements. Before thermal breakthrough, no oscillation were observed with both coarse and fine mesh. However, shortly after the heat front reached the right-hand side of the boundary, small oscillation started. The small oscillation of the nodal solution were found in the coarse mesh, and oscillation increased here, and oscillation increased late stage after thermal breakthrough, and finally reduced to reduced reaching a steady with a constant uniform temperature of 20 degrees centigrade. But the oscillation did not happen, as you can see, in a fine mesh. In a fine mesh with linear elements, and so as a nice result, we can say that the coarse mesh with linear elements could be used for determining of the time required for thermal breakthrough in open loop system, but it should not be used to predict the temperature distribution after this phenomena take place, because the solution is affected by a considerable oscillation. Here we can see the impacts of the quadratic elements. So as same as the previous ones, the left one is for the coarse mesh and the right one is for the fine mesh, but the difference is it's just an element type, which in this case is the quadratic elements. So clearly have a much better ability to solve highly convective heat transfer problem with a much smaller numerical oscillation. Just later we can see here in a course and so it is illustrate that coarse mesh with quadratic elements can be utilized in a simulation of an open loop systems as effectively as fine mesh with linear elements. So here we can see the modeling consideration is the model is a two-dimensional coupled thermohydraulic analysis, and using Imperial College Finance element program for modeling, and the element type, element size, and time step size were varied. And the theta method was applied with the backward difference scheme, and the calculation maximum P number is 60 for the coarse mesh and 16 for the fine mesh. Here you can see the open loop system, which is simulated. There is no water flow across the boundary of the mesh. A thermal boundary condition in the form of constant temperature was prescribed at the injection well, which is 20 degrees centigrade, as I mentioned before. And then while at the left, right, and top mesh boundaries, the initial temperature of 10 degrees centigrade was kept constant. And at the abstraction well, where the water is leaving the mesh, the coupled thermohydraulic boundary condition was applied. And the thermal boundary condition were applied after establishment of a steady state water flow between the two wells. So here you can see the details of 6 different analyses in this table. So the case A and B both are the coarse mesh, and the rest are fine mesh. And then you can compare the P numbers. The bigger P number shows for present for the coarse mesh, and then the 16 is for the fine mesh. Half of the analysis cases were linear, and then the rest were quadratic. In this case, we can see the actually compare the effect of element size and the temperature at the abstraction well. So we're comparing the analyses B and D, with the B is the coarse mesh, and then the D is the fine mesh, and the rest of the properties are the simple. I mean the element types and the time steps are the same. Is the only thing that's different in two analyses is the element size. So as it can be seen in this picture, we can say that when we are using the quadratic elements type, as I mentioned before, element size and the PE number have less impact on result, and then the results are so close together. So even if is the coarse mesh or is a fine mesh, so if we have linear elements, it impacts on the result. But for the quadratic type of kind of the elements, is not going to make a big difference in the results. Here we're going to compare the effects of element types on the temperature at the abstraction well. Analysis C is linear and D is quadratic. And we can investigate the effects of the element type in this case, and both use a fine mesh here and the same so as it can be seen for the fine mesh, for both linear and quadratic elements, we can get good result, even better than the previous ones, because it's almost match. The two results are so close, and that's because of the using the fine mesh. So in general, if we use fine mesh, we're going to get better results because it's with a better is a better way to describe all details when we have the fine mesh. So the element types here is not impact on it's not a big there's no is not in the on the temperature at the abstraction well. So because both are the fine mesh. So here we're comparing the effects of time step size and the temperature as the abstraction well. The analysis the delta T is 180 seconds, and then for the F is 600 seconds. Both use quadratic elements and fine mesh, but the only difference is in time steps. And here we can say when we have the fine mesh in general, we can give same result even with different time steps, and also better result when we have comparing when we have the coarse mesh. To summarize the result and referring to previous charts, these results can be conducted. So the predicted time to thermal breakthrough are almost the same for coarse and fine mesh. So for example, for the B and D, both were quadratic, and then you can see the times are almost the same. And then the P number has not a significant effect on the temperature evolution of the abstraction well in this case, especially when we're using the fine mesh. And then comparing analysis C, which was linear mesh, and then the D, which was quadratic mesh, illustrate that the effects of element types is very small when we have fine mesh in both analyses. And this study actually provided numerical facilities which are required for performing coupled thermohydraulic finite element analysis. These facilities were implemented in ICF EP finite element, which is a finite element software, and the validation shows that an acceptable match between the software result and the corresponding analytical solution for heat flux through the conduction and convection. And the key conclusion of simulating highly convective heat transfer with Galerkin finite element method is, we can say that the PE number is a useful indicator, and it can be used as a measure of the element size, and that is required to prevent oscillation. And the result improved the decrease in PE number when quadratic elements are used, and it has been indicated that the element types has no significant effect on the thermal breakthrough, especially in a fine mesh. And finally, we can say that the Galerkin finite element method, as implemented in ICF EP software, can simulate highly convective coupled thermohydraulic problems, like well Doppler system that we as we can see in this case for the open loop system. And these are the references that I used for this study. And thank you for your time and attention.
Yeah. That too, but I'll start my presentation afterward, after her presentation, because her presentation was about more about the theories and the result from the paper, but my presentation will be about the calculation, like simple calculation, simple, yeah. So it's a little like same topic, but a little different approach.
That's why we couldn't have the same same presentation together in the same slides.
So you think yeah, yeah. Yeah.
For the fine and the coarse mesh, so basically it's the difference between the element size. So as I mentioned in my presentation, the PE number is a good indicator that shows the which is which. So if this number is in this case was the 60, the bigger number was presenting the coarse mesh, and then the 16 one, which was the last one, presented the fine mesh. The pickle numbers, just let me. Actually,
I think you have it in your slides.
yeah, I had it in my slides, and so I didn't mention the formulation for the P numbers, so it's going to be too long if I wanted to go through. So basically, if we have a small meshes, we can have, we need to spend more time to analyze this because it's more complicated, but we can reach the better result. But if we have the bigger elements and the coarse mesh, we can reach the result sooner, but it's not a good result. It's not in comparison, the fine mesh is not a better compact with the reality case. Yeah, it's yeah. So basically, the P described is not actually advection, as the describe a ratio between the convection and conduction, and so in the formulation. So if I Yeah, it is a physical property. There was a formulation to calculate the P number, and then in that equation, it was a component of L for calculating the P number. So if the L is the bigger, it means that we have a coarse mesh, so we have a bigger P number, and yeah. Yeah, exactly. It's computed for the elements. So based on it depends on the density, it depends on the surface capacity, the velocity, and the conductivity, and also the most important one is the length of the elements. So if you have the coarse mesh, we're going to have a bigger P number, and then which illustrate the conduction is dominated in our problem, in our case. But so I think I didn't get your question. Yeah, is not a specific value, is kind of a try and error to find a best PE number to get a better result. I mean, if is not a good idea to always have a fine, extremely fine mesh, because the calculation and it's going to be it takes so long to analyze a fine mesh in comparison to coarse mesh. So if we could find a good PE number in order with a coarse mesh, reduce the oscillation without having an extremely fine mesh. Thank you.
It's okay now. Let's see my screen.
Yes, it's okay.
All right. Hello, everyone. So my topic will be about the 2D transient heat transfer by conduction and by implicit finite differential method. And I will use MATLAB. We will create a MATLAB GUI to illustrate the problem. So for the content, I will go very short on the content, and the remainder time will be for the MATLAB. So firstly, I will introduce the differential equation of heat transfer, which is one of the very common equations in a couple thermal hydraulic mechanical problem. And then I will show the method to convert the differential equation to a more simple algebraic equation, which is used by explicit method. And next, I will introduce the geometry as well as the boundary conditions for the MATLAB GUI that I created. And finally, there is the demonstration of the code. So usually in 3D, the governing differential equation for heat transfer will be the equation of T, the temperature with variation of space and time, where we have a Q, Cp, and rho and kappa are all the parameters relating to the equation. But with some assumptions like the dimension just unity, so we only consider the 2D in this problem. And also the isotropic thermal conductivity. So the kappa will be just the one unique value, and there's no heat source to consider in this problem. So finally, we will end up with the equation of heat transfer like this. And this is the equation that I usually use in the TSM coupling problems. So to solve this kind of equation numerically, people usually we have many we have various methods. So one of that is this implicit method. So we have the equation here, and using the implicit method, we can symbolize the equation to have the temperature variation with time and space very simply, as shown in this green box here. Take one thing should be like the attention should be taken to this equation is that the Rx and Ry is very important parameter to define the stability of the numerical analysis of for the app. So no matter how much time decreased or space you use, it should be meet this requirement that Rs or Ry should be smaller than 0.5. And for the geometry and boundary condition of the for the numerical analysis, I let's assume that we have a plate, any kind of material like copper or any. So we have the top and the top, left, right, and bottom temperature with a fixed temperature, and the dimension of the length and height of the materials is L and H. So what we want to have is the temperature variation with time and the X and Y axis of the materials. And in the right hand side, you can see that for the simulation, we should decrease the domain into various several nodes, so that we can use our implicit method to calculate the temperature variation distribution within the domain. And the conversion criterion here is I chose it to be 0.0001. It will depend. You can choose whether it will be 0.5, 0.00, any you want to. Like the point is, this conversion criterion will decide when your transition state will become steady state. So the temperature will not change with time anymore, and the difference between 2.0 of temperature with of time will be related to the conversion criterion. So for the MATLAB demonstration, I will change my screen to the MATLAB. So want to check it. Anyone can see my screen now?
Yeah.
So the MATLAB GUI is the very nice function in MATLAB that allow you to design an kind of application to visualize, to make it easy to operate your code. And here we have the initial and boundary condition. Boundary condition symbol. I will take we will have the initial temperature in our domain is 20 degrees, and the top is 0, bottom is, let's say, 60 degrees, 10 and 10. So for the geometry, we will have a small plate of material at 5 centimeters, and we will divide the material into like 21 nodes for each dimension, and the thermal diffusivity for the calculation. In here we have 3 type of material: air, copper, or water. As you can see that anytime I choose the material, there will be a note that tell us that whether if we choose this geometry and also the time, the value of numerical stability will change, and we have to make sure that the value we choose here create a value of FO. I call it FO here should be smaller than 0.5. For example, here we have copper. DT is 0.01, and the total time is 50 seconds, and conversion criterion here is 10 power minus 4. And so I will start the app to see what the temperature will change with time. Let's start again. Is it too fast? Okay. So we can see here that when we have the initial temperature and boundary condition with all of the value that we all set, we will have the time, the temperature change with time and space, and the time indicate here is 0.5 seconds. It means that after 3.5 seconds, our domain, our system become steady, and it's now in steady state, and the temperature will no longer change with time. Let me change to another 10. And keep the same parameters here. So again, we see we change the boundary condition, and we have the time distribution in the domain change with the time for the time to reach the steady state is even though we set this time in 50 seconds here, but after only 8.5 seconds it reached the steady state, and we stop running. And there's one more feature in the app here that we have a monitoring point that relate to this figure. Like say if with X and Y is the coordinate in our domain, is the 11th node, and let's say another point in the 15th node, and run. So we see here the temperature change with time, and it get level up around like 9.5 seconds, and it doesn't change anymore. It meet the conversion criterion that temperature no longer change. The difference between the temperature changes is smaller than 10 power minus 4. So okay. So some concluding remarks and some future and recommendation for the future works here. Like the MATLAB was used to show, we can use the MATLAB to show the 3D transition heat transfer in this case, isotropic media using the explicit FDM. And for the FDM, the stability condition is very important that we choose the delta X, delta Y, and delta T, so that the value of R should be smaller than 0.5. And the future works will attempt to upgrade the code to solve a more complex problem like thermohydric process, where the pore pressure and displacement and temperatures is all together a function of X, Y, and T and time. So that's the end of my presentation. Thank you very much.
I have a question. I'm sorry. I know what if we have like boundary condition with different temperatures. I wanted to know what if we have different temperature, like in the left and right. So here you simulate the left and right have the same temperature. So how change if we have different temperature? Okay.
I mean,
Like
I chose the very random value of boundary condition. So we can change the value here. Any value we want to. It's long, but it's reasonable.
I have a question.
Shouldn't be like something like.
Since you're at the boundary condition values there, what if you put a negative value there in temperature, say -1, -2? How does the
I didn't check the negative temperature. Yeah. Okay, let me check here.
No, I mean like even the initial temperatures too. Like I just want to see what the model does, right? Like, did you program it for that, or?
I'm sorry. Could you speak a little louder, please?
Like the programming, I'm saying, like, did you account for the change in the negative values? Like, how does the problem become when you start with an initial temperature that is negative, let's say?
So I think because programming is just about a number. So
Yes. Yeah.
I think I think the negative value is will not make the app function fail in functioning. So but let me check. I think it's not it's as long as there's any like mathematically related correlation that doesn't allow you to have a boundary condition that a negative boundary condition value. In that case, when you run with a negative value, it will fail, I think. But for this one, I think it's worked well. So it works. Yeah.
That's a pretty impressive thing that you did. So cool.
And for sorry, for clarification, this is not the first of its kind. So there's many other researcher or it is conversion the global chain. So it's it's a global yeah, that's it. For the conversion question, I will check in the total domain in every single node, but the most point here is it's just for illustration, like to visualize. Yeah, exactly. Thank you.
Professor, yeah, I think he's not here, so because I can't see the name of the.
Thank you, Professor.
Thanks, Professor.
Thank you,
so
Professor.
much, Professor.
Thank you, Professor.
And
And it's going to be online, right?
So you give us the exam, and then we submit it like 7 days later. Or something. No, thanks. No. I think we're with it. We're happy.
So we're gonna have a harder question in 7 days in comparison with 3 hours. So prefer.
Okay, have a good night. Thanks. Yeah.
Thank you.
We're ready.
Thanks. Have a good night. Yeah.
Oh yeah.
Oh no, no.
Okay. We'll see you next week. Thanks.
Bye.
Bye.
Thank you. Good night, everyone. Thank you very
Good
much.
night, everyone.
Good night, everyone.